I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Timely. We'll look at two interesting problems from the 1600s, which have the remarkable feature of having the same solution. When announcing the result, the mathematician Johann Bernoulli said, "You will be petrified with astonishment at the solution." Well, it probably won't hit you quite that hard, but the result is truly surprising. And it does seem to have stunned the Cardiff giant. This, by the way, was a hoax created in 1868, implying that giants used to walk the earth. The first problem is called the tautochrone problem. The etymology tells the story. Taut for same, think tautology, and chrone for time, think chronology. We are looking for a curve with a same time property. That is, we want a two-dimensional curve such that a bead sliding down a frictionless wire acted on by gravity takes the same amount of time to reach the end no matter where it starts. The curve should look something like this. Starting the bead at the top, blue, gravity will cause it to pick up speed quickly. On the other hand, starting the bead nearer the bottom, yellow, it has less distance to travel, but it will not pick up as much speed because the curve is closer to horizontal. The extra speed gained at the top balances the extra distance the bead has to travel. You can see a nice animation of this on Wikipedia. Equations for the exact shape of the tautochrone curve, called a cycloid, were found by Christian Huygens in 1659. In parametric form, the equations are x equals r times theta plus sine theta, and y equals r times 1 minus cosine theta. There is a nice way to visualize the shape as a cycloid. To trace out a cycloid, pick a point on a circle and follow the path of that point as the circle rolls along a straight line. To get the tautochrone problem, you'll have to turn this one upside down. Well, that's a clever little problem. The second problem we'll look at is the related brachistochrone problem. Brachistochrone meaning shortest time. Given 2 points, what is the shape of the two-dimensional frictionless wire that the bead slides down to reach the lower of the 2 points in the shortest amount of time? This was stated in the grandest style possible by Johann Bernoulli in 1696 as a challenge to the world's best mathematicians. Kind of a mathematical throwdown. The rules were that you only issue such a challenge problem if you could solve it yourself. Bernoulli was undoubtedly hoping that no one else could solve it so that his solution would mark him as the world's best. Here is his statement. I, Johann Bernoulli, address the most brilliant mathematicians in the world. Nothing is more attractive to intelligent people than an honest, challenging problem whose possible solution will bestow fame and remain as a lasting monument. Following the example set by Pascal, Fermat, etc., I hope to gain the gratitude of the whole scientific community by placing before the finest mathematicians of our time a problem which will test their methods and the strength of their intellect. If someone communicates to me the solution of the proposed problem, I shall publicly declare him worthy of praise. Well, I kind of agree with it's very nice to have an excellent problem to work on. And mathematicians do love the challenge of a hard problem. Not so sure about the rest. Alright, so what is the brachistochrone shape? Here are 3 potential shapes. The straight line is the shortest path, but the curved paths would allow the bead to pick up more speed and reach the endpoint faster. The curve with the initially vertical drop would produce the most speed, so you might suspect this is the best curve. And it looks a lot similar to the tautochrone curve. And in fact, it is. The exact same curve, though the solutions can use different portions of the curve. The tautochrone always finishes at the bottom, horizontally, and the brachistochrone always starts at the top, vertical, and may actually go past the bottom and swing back up. 5 solutions were presented, including one by Johann's brother Jacob, one by the great Gottfried Leibniz, and one by an anonymous author. Bernoulli deduced, however, that the anonymous author was in fact Isaac Newton. Bernoulli wrote, "We recognize the lion by his claw print." Newton had used his recently developed calculus, along with some newly developed ideas related to the calculus of variations, to find the solution, purportedly on the very night that he received the challenge problem. Bernoulli published the solutions as promised. However, he covered up a flaw in his own solution by using the solution technique of his brother. Brother Jacob retaliated by solving a harder version of the problem, and the two brothers and succeeding generations of Bernoullis spent the rest of their lives arguing about who was better and who did what. The battling Bernoullis were something. The Todochrone and Brachistochrone have the exact same shape. Are you petrified with astonishment? Probably not, but I think it's very cool that the same shape gives the fastest transit and has the same time property.